Hello everyone, let's go ahead and talk about calorimetry in this section. So in calorimetry, we can basically find out heat lost or gained during a reaction. So the equation is given as Q equals Cm delta T, Cm delta T, or sometimes students would love to rearrange it as Q equals mc delta T. That looks like Q equals m cat. So here Q is the heat lost or gained, C is the specific heat capacity, m is the mass in grams, and delta T is the temperature difference within final and initial temperature. Okay, now here something that you are going to learn new is the specific heat capacity. So what is specific heat capacity? The definition for the specific heat capacity is if you have a 1 gram of a sample, could be 1 gram of water, 1 gram of a metal or wood or anything, you have 1 gram, let's say you have a temperature 22 Kelvin, and you take the same 1 gram, you want to raise the temperature by 1 Kelvin unit, and this become then 23 Kelvin. Again, still it's 1 gram. What is the heat required? So specific heat capacity of a substance is the quantity of heat required to change the temperature of 1 gram of the substance by 1 Kelvin unit. Okay, so it's measured in joules, so the units are going to be joules per gram per Kelvin. Okay, so the next table shows us specific heat capacities of some substances. You can see that metals like aluminum, graphite, iron, copper, gold, they all have specific heat capacities less than 1. And then water 4.184, another liquid, ethyl alcohol, ethylene glycol, they are 2.46, 2.42, and some other materials as well. So in this table we can see water having a higher specific heat capacity, which is a really good thing for our survival on planet, because most of our waters, seas and oceans and all of these are made up of water, and we have a lot of heat getting from the sun's light, right? So since water has a higher specific heat capacity, so it can absorb water, it can absorb heat but not changing the temperature much because it has a higher specific heat capacity. Okay, and metals also have low specific heat capacity. That's why you put a pot or pan on top of a stove that is made up of metal, will heat it up really quickly. But if you have water, you will say it will take some more time for water to get heated up, because water has a higher specific heat capacity. Okay, now with the equation that we have learned earlier, Q equals mcat, we can find out either a specific heat capacity or a heat required for a certain reaction to take place. So let's look at this example. A layer of copper welded to the bottom of a skillet weighs 125 grams. So we know the mass of this skillet is 125 grams. That's going to be M. How much heat is needed? So we want to find out Q is what we need. We are given mass to raise the temperature of the copper layer from 25 to 300 degrees Celsius. So then the delta T is going to be the temperature difference, final temperature 300 minus the initial temperature 25 degrees given in Celsius. We know the delta T. Specific heat capacity of copper we can find from the given table, which is 0.387. 0.387 is the specific heat capacity for copper, joules per grams per Kelvin. Now we can find out Q because we know M, we know C, we also know delta T. Okay, so this is how you're going to be doing it. We can calculate delta T and then the Q. Delta T final minus initial, 300 minus 25, that's 275 degrees Celsius, which is also similar to 275 Kelvin. So because how do you convert Celsius to Kelvin? Now if you take 300, you're going to be adding 273.15 to convert it to Kelvin. So that would be 573.15 Kelvin. And then you take 25 degrees Celsius. If you want to convert it to Kelvin, you're going to be adding 273.15. That will give you 298.15 Kelvin. So the difference between 325 is 275. Now we converted them to Kelvin. Let's see what's the difference after you convert it to Kelvin. So then the delta T going to be 573.15 minus 298.15, and these are in Kelvin. So what's the difference going to be? 573 minus 298. To do the calculation with your calculator, it would still be 275 Kelvin. 275 Kelvin. So if it involve subtraction involving Celsius, Kelvin value also going to be the same. Okay, so you do not need to convert it to Kelvin. You can keep it in Celsius if it involves subtraction or addition. But if it involves multiplication or division, you need to convert it to Kelvin if needed. Okay. Now, I just wanted to show you that it's okay keeping in Celsius. Okay, so then we can calculate the heat required to raise the temperature from 25 to 300 using Q equals Cm delta T. Specific heat capacity is given, joules per grams per Kelvin, and then the mass is 125 from the given question, and then the delta T 275. So you multiply all these three to find out the Q, which is 1.33 into 10 to the power 4 joules. So that's how you calculate a heat required to raise the temperature of the copper layer from 25 to 300 degrees Celsius using Q equals mc delta T. Okay. Now, if you want to find out a specific heat capacity of a substance, we use the coffee cup calorimeter. Now, this diagram represents the coffee cup calorimeter, which is made up of a styrofoam cup. Okay, so this is a nestled styrofoam cup. This is a cross section of that. You can see the sample like a metal block, and then you can also put a thermometer inside. There is a stirrer. There is a cork stopper, so the heat would not escape from the system. And then you can also have water inside. Okay, so how are we going to use a coffee cup calorimeter to find out a specific heat capacity of a metal sample? Let's look at that with this problem. Determining the specific heat capacity of a solid. You heat 22.05 gram of a solid in a test tube to 100 degrees Celsius. Okay, so what you're going to do, you take a test tube, you put the piece of metal here, you put it in a boiling water, and then you boil the water. You're going to boil it for about 10 minutes, and then you can also put a stopper. And during that time, water boils at 100 degrees Celsius. When you boil it for 10 minutes, we assume the inside the test tube there is our sample, metal sample, that also reaches the 100 degrees Celsius. And then the mass of that sample is 22.05 grams. You see, that's what it says. You heat 22.05 gram of a solid in a test tube to 100 degrees Celsius. That is going to be the initial temperature of the metal. And then add the solid to 50 gram of water in a coffee cup calorimeter. So you guys saw the coffee cup calorimeter. In the calorimeter, you can have 50 gram of water to begin with, and you add the solid, which is at 100 degrees Celsius. You take this solid over here, you carefully with a tweezer, you're going to put it inside here to the water. Before you put it into water, you want to make sure that you take the temperature of the water. So the water temperature changes from 25.10 degrees Celsius. That is before you put the metal piece. Okay. And then once you put the metal, what's going to happen? Now the metal is hot at 100 degrees Celsius. So metal is going to lose heat to the surrounding. So what happened to the water in the coffee cup calorimeter? Water will heat up, right? Because the metal is losing heat, water will absorb heat. So this is the initial temperature of the water, and then you monitor with the thermometer to see what is the highest temperature that it reaches. And in this case it had reached to 28.49 degrees Celsius. Find the specific heat capacity of the solid. Okay, you will also going to be doing an experiment similar to this concept when we do the experiment of the enthalpy calorimetry. Okay, I hope you understood the question. So the coffee cup calorimeter that's being used is similar to this. Okay, you have the thermometer, you have the sample, you put it inside and then record the highest temperature it reached. Now we want to find out the specific heat capacity of the solid. What are we going to do? So plan. We are given the mass of the solid. We know the mass of the solid 22.05. And we also know the mass of the water 50 grams. And we can find the temperature change of the water and of the solid by subtracting the given values. Okay, delta T. So we always use final temperature minus the initial. Now what's going to be the final temperature of the metal? Remember, you took the metal at 100 degrees Celsius, you put it into the water, and then metal lost heat and it reached to a certain temperature. The water reached to a certain temperature which is 28.49. At that temperature, water and the metal both have the same temperature. We say that they are at thermal equilibrium. So the final temperature for the metal as well as for the water both going to be 28.49. Okay, and then what would be the initial temperature of the metal? It would be 100 degrees Celsius because we heated up initially to 100 degrees. And then what about the delta T for the water? So this is what we are doing here. For the final temperature of the water, again going to be 28.49. Before we put the metal inside the water, initial temperature of the water is 25.110. So the difference will give us the delta T for the water, 3.39. And then delta T for the solid would be final temperature minus the initial. Final temperature for the solid also 28.49. Initially we heated up to 100. So the difference for that metal solid is negative 71.51 in Celsius. We can directly take that difference as Kelvin because I showed you in the earlier slide that Celsius and the Kelvin difference would be the same. Okay. Now with the temperature information, we found the delta T for the water and delta T for the solid. Our goal is to find out the specific heat capacity for the solid. So what do? We're going to be using equation Q equals mc delta T. Remember I told you that the metal is losing heat, water is absorbing. Okay, so if metal lost a certain amount of heat, who absorbed it? Water absorbed it, right? So when it reaches the highest temperature at that time, the heat lost by the metal equals heat absorbed by the water. Q metal equals Q water. So the metal lost heat. Metal lost heat. Because metal lost heat, the sign for the metal for the lost heat is negative, and then the water absorbed heat. So the water will be positive. So the same quantity, but opposite signs. Okay, and we know Q metal or Q water, we know we can use MC delta T. So Q metal, if you write down the information for Q metal, that would be mass of the metal, specific heat capacity of the metal, times delta T for the metal, they are going to be negative, equals mass of the water times specific heat of the water times delta T for the water. Now we know the mass of the metal. We don't know specific heat capacity, but we know delta T for the metal. We know the mass of the water. We know the specific heat of the water, 4.184. We also know delta T for the water. With the known amounts, we can find out the specific heat capacity of the solid. Okay, so the Cm, or the C solid, which is like the Cm in my case, it would be specific heat capacity of water. Remember, we need to carry that negative sign over here, so that negative sign right there. Specific heat capacity of water times the mass of the water times the delta T water, you divide it by mass of the solid, which is the mass of M represent the solid, delta T of the solid. Okay, so once you set up your equation, then you plug in the numbers. Specific heat capacity of water 4.184. Remember, we have this negative sign here. And then the mass of the water 50 grams. And delta T we calculated 3.39. Mass of the solid 22.05. And then remember the delta T for the solid we calculated, and it came to be negative 71.51. So we have a negative, two negatives. It's a division. So they get cancelled and become positive. Excuse me. And then you just have to do the calculation with these numbers. And then Kelvin will get cancelled. And then the grams will get cancelled. And you will have the answer in joules per grams per Kelvin as a specific heat capacity of the solid. 0.450 joules grams per Kelvin. So that's how we use a calorimeter to find out a specific heat capacity of a solid. Okay, and your experiment of enthalpy will also be similar to this calculation. And if we want to do a little bit more sophisticated work, we can use this bomb calorimeter. It measures the heat release at constant volume, but we're not going to deal with that. Okay, and maybe we can stop here and start the next section later. Okay, I'll stop here for now.